Now, this is another topics in which we will use Gauss's theorem. So, this is a infinite plane sheet. It is uniformly charged. We have to calculate the field at a distance of r. This is our infinite sheet, and it has this uniform surface charge density. Now let us take sigma is the surface charge density. Surface charge density. It means that charge upon area. Now its unit will be coulomb per meter square. Coulomb per meter square. If I go in the SI system, coulomb per meter square. Take a symmetrical Gaussian surface. In this case, we can use cylindricals. We can also use cubical surface also. So suppose I have taken say a cylindrical surface. Take a cylinder whose length is twice r. Half will be right of this and half will be right of this. So the total charge included by this Gaussian surface is equal to only charge on this portion. Charge on this portion. Let us suppose A is the area of cross section. Its area of cross section is equal to A. Area of cross section so total charge inside of this one will be, now you know that sigma charge on unit area and its area is A. Now total charge on this will be sigma times of this one. This will be the charge on this. Only inside of this cylindrical Gaussian surface is sigma times of this one. Now we know that this is a closed Gaussian surface. This closed Gaussian surface has three surfaces. One this plane surface, another plane surface, and this is the curved surface. Now this will be the curved surface. So we know that any charged conductors which has electric fields away from this one. So electric field due to this plane sheet will be away from this one. It means that at the point of A it will be outwards, rightwards, and the P dash it will be leftwards. So we know that its area vector will be in the directions of, suppose this is a ds1, in the direction of E, and its area vector will be in the direction of E also. So it is ds2. Now another curved surface will be this one. This is the curved surface. If you take a small area of this one, its area vector will be in upward direction. You know that at this point electric field away from this one. So here electric field in the rightward, suppose, not suppose, it is exactly the angle between E and ds3 is equal to 90 degree. So there is no contribution to cos 90. Cos 90 will be 0. Therefore there is no contribution due to the curved part in the total flux. So in this case, here electric field parallel to ds1, electric field is parallel to ds2, and electric fields normal to the curved part. This E is perpendicular ds3. So only the electric field will be passed through these two areas. There is no electric flux only. There is no electric flux through the curved part. So therefore there is no electric field through the curved part, because in that case angle between area vectors will be the normal to this curved part, and electric field which will be along the axis of this cylindrical. So there is no electric flux passed through this curved part. Only the electric flux passed through will be this plane sheet and this plane sheet. Now therefore electric fields are due to E times of ds1, total electric field will be E times of ds1 plus electric field times ds2 plus E times of ds3. There is no electric field due to ds3 curved surface. Only electric field will be this one. So now it comes out. ds1 has a total surface area A, and we know that EDA cos 0 degree. Same way is here. EDA, there is no flux pass through this one. Total flux will be twice EA. Twice EA. We already explained the angle between them is 0 degree. Therefore, E dot ds1 is equal to E. ds1 has the area of this one. Area of this one ds1, and this is ds2. E times of A cos 0 degree. Cos 0 degree has the value 1. Similarly, E times of ds2, electric field along this one, ds2 along this one, so angle between them is 0 degree. Therefore, it will be ds2 as the area. Total area of this one is A and cos 0 degree. Now it comes out E times of A. E times of A. Now total electric flux. This is our electric flux. Phi E times 2EA. Now according to the Gauss's rule, Gauss's theorem says that total flux pass through a closed surface. This is our closed Gaussian surface will be total charge included by this Gaussian surface divided by the epsilon naught. Now therefore our value becomes here according to Gauss's law, phi is equal to charge upon epsilon naught. The total charge inside of this one will be on this region, charge sigma times of A divided by epsilon naught. This is our equation number 2, and it is our equation number 1. If I place phi twice EA in this place, I will get twice EA is equal to sigma A times of epsilon naught. A is cancelled out from here. Electric field comes out sigma divided by 2 epsilon naught. So therefore, this is our final formula. Electric field due to a plane sheet. Electric field due to a plane sheet. It not depend on any value of R. This is not depend. It depends only sigma, the charge density on this plane sheet. So at any distance r, from this plane sheet, the value will be the same. In the left hand side it has direction leftwards, and right hand side it has a direction rightwards. So in this way we have using the Gauss's theorems very easily to find the electric field due to this infinitely large plane sheet.